I think the most striking thing that we humans have learned so far from studying our universe is that we need to think big. Because we've again and again and again underestimated not only the size of our cosmos, but also our ability to understand it. And it's interesting to ask, why is it that we humans have been able to figure out so much about the cosmos? Much, much more than we dreamt of thousands of years ago. Part of the reason is obviously that the human mind is really amazing. But I think there's more to it. There are two very powerful ideas which are sort of form the cornerstone of modern science. One of them being make experiments. Get data from nature and use those clues. And the second idea is that whenever we have made an experiment, we should take the data, numbers that we've measured, and try to make mathematical models of them. We've taken this so much for granted that we often forget to ask why it works so well. But I think it's quite striking that the real reason that we humans have figured out so much about our universe is because our universe seems to contain all these mathematical clues and patterns and regularities that we can tap into with mathematical equations and get better at predicting things and ultimately figuring out how to build things. This is an old idea. Already Pythagoras in ancient Greece talked about our universe being ruled by numbers in some sense. And during the Renaissance, Galileo wrote that our universe is a grand book, written in the language of mathematics. But what do we mean by this? If I look around myself in the room here, I don't see any numbers written in this on the ceiling or in the sky. Where is all this math that people are talking about? Well, we see a lot of it if we look for patterns. If you throw something, it moves in a parabola. Give my simple equation, y equals x squared. If you look at how things orbit around in the sky, whether it's orbiting a star or a black hole, it's always going in the same shape, an ellipse. And that's linked to the parabola because the edge of the ellipse is shaped like a parabola, roughly. And we've gradually, during the centuries, found more and more patterns and shapes like this that we've been able to capture with simple mathematical equations. And it's really interesting if you look at some great discoveries, like the discovery of the planet Neptune, the discovery of the radio wave, the discovery of the Higgs boson. With what tool were all of these discoveries made? With mathematics. With the planet Neptune, there was an astronomer, Urbain Le Verrier, who noticed that Uranus wasn't orbiting quite according to the equations of Newton that it was supposed to. So he wrote this letter to this astronomer in Berlin, Gall, and said, point your telescope at such and such a place in the sky at such and such a time, you will there find a new planet. The guy who got this letter maybe thought that Le Verrier was nuts, but he looked, boom, there was Neptune. A few decades later, James Clerk Maxwell took all the known facts about electricity and magnetism and unified them into the Maxwell equations. He studied the math more, and he made this prediction that if you build a certain kind of device, you can use it to transmit what we now call radio waves. That can let us send information at the speed of light through empty space, through walls, and now we all have cell phones in our pockets, being predicted through mathematics. And most recently, Peter Higgs took the most advanced mathematical description ever of physics, the standard model of particle physics, and did math, and predicted that if you build the most advanced scientific instrument ever built in Geneva and crash particles together with it near the speed of light in a certain way, you will there discover a new particle. We built it, boom, there it was, and Peter Higgs won a free ticket to visit my hometown of Stockholm as a result. Right? So mathematics is proven very powerful for physics. But why? Everything I've said so far is fairly uncontroversial, but this is where it really gets controversial and interesting. Some people think this means nothing. It's just a fluke. It's the way it is. We should be grateful for it, but it has no explanation. Some people think maybe the explanation is just that we humans kind of sort of invent math. It has something to do with our brains. In my book, Our Mathematical Universe, I explore the full range of possible answers to this question. And I also explore the most radical, extreme answer on the other side, saying that not only is this not meaningless, but it actually means something very profound. I explore the idea that it means that our universe is really very mathematical, in fact completely mathematical, in the sense that our universe is a mathematical structure. It has no properties at all except mathematical properties. And when you first hear this, it sounds very crazy and implausible, because again, our world doesn't seem particularly mathematical at all. But when we look at our world as physicists, we get reminded of the fact that everything in our world, including my book and me and everything else, is made of these elementary particles, like electrons and quarks. And what properties does an electron actually have? It has the property -1, 1/2, 1, and so on. Numbers. We physicists have come up with geeky names for these particles, like electric charge and spin and lepton number, but the electron doesn't care what we humans call it. Those are just human words. The properties that it has are just mathematical properties. And as far as we can tell, neither the electron nor any of the other elementary particles have any properties at all except for mathematical properties. So all of the building blocks of nature, all these elementary particles, are purely mathematical objects in the sense that they, as far as we can tell, don't have any properties at all except mathematical properties. That's the stuff in space. But what about space itself? What properties does space have? Well, it has the property 3, for example. 3 is the largest number of fingers I can put perpendicular to one another. And again, we physicists have a geeky name for this. We call it the dimensionality of space. But space doesn't care. That's just the word. The property is 3. It's a mathematical property. Einstein discovered that space also has some other properties, curvature and topology, but they're also completely mathematical. So if you accept this notion that both space itself and all the stuff in space has no properties except mathematical properties, then it starts to sound a little bit less insane that maybe everything really is mathematical. Now, what does this actually mean if it's true? To me, it actually means very good news for physics, because if it turns out that nature has some properties which are fundamentally non-mathematical, that means that physics is going to be ultimately doomed. One day we'll hit a roadblock beyond which we just cannot proceed further in understanding the cosmos. We'll still have big things we can't understand, but we will have run out of these mathematical patterns to discover, because there are no more, and we'll be forever stuck. But if I'm right about this, then there is no roadblock. There are none of these non-understandable, non-mathematical properties, and our ability to ultimately understand our cosmos is only going to be limited by our human imagination, which I think is a much more optimistic viewpoint. Of course, which way it is, we don't know at this point, but I think it's actually a very useful and healthy working assumption that there is no roadblock, because as we all know, there's no better guarantee for failure with any endeavor than to have some kind of starting principle, the assumption that what you're trying to do is impossible, so that you therefore never even try. So if we for a moment explore the hypothesis that this is true, that it's all mathematical, it's fun to think about other implications of it. First of all, it suggests that the other big areas of science right now that we don't understand, for example, consciousness, are also subjects we can keep studying mathematically, and maybe with a hope that we can actually ultimately one day understand them. I was organizing a physics conference recently where we had some fantastic neuroscientists like Giulio Tononi and Christoph Koch, who are actually pursuing this idea that consciousness, the reason why you feel that there's a movie in your head, the reason why you can feel love and feel the fragrance of a rose, the color red, also can be understood in terms of mathematical patterns in the information processing in your brain, for instance. We'll see whether their theory ultimately pans out, but this is the sort of thing that one has hope for. Could certainly be possible if it's all mathematical. If our universe really is mathematical, it also gives us yet another multiverse. Beyond the level 1 multiverse of a bigger space than we can see, and the level 2 multiverse, where some of the laws of physics apparently differ, and the level 3 multiverse of quantum mechanics, it also gives you a fourth and ultimate multiverse where every possible mathematical set of physical laws actually corresponds to a real universe. If our universe really is mathematical and the level 4 multiverse exists, I feel that that would also be good news for physics research, in the sense that it would let us open up a second front. If you're trying to build a bridge across a river, the way you usually do it is you start building from both sides and then meet in the middle. It's much quicker than building only from one side. And what we've traditionally done in physics is we do the empirical approach and build telescopes and microscopes and expand our empirical knowledge and try to find mathematical models of this. But what we can also do now is the opposite approach, where we write computer software to simply map out an atlas of all mathematical structures that exist, and look at this mathematical landscape of all these different mathematical universes and ask, okay, where are we in this landscape? Oh, we're probably not there, it can't be over there, it can't be over there. Oh, but here maybe is a promising sort of neighborhood. Maybe it's in one of these regions. Then you can study these mathematical equations more carefully and try to find out whether that actually is where we are. The ultimate goal being to find a match where we can say, this mathematical structure here corresponds exactly to what we're seeing with our telescopes and our microscopes. And now we know where we are in this big reality.